All right, so now we are ready for looking at an example over here. And in this example here, I call that example 1. Let's just learn how we can identify and sketch the graph of. So the plan for this particular example here, I am going to give different various equations here. And of course, these are intended to be equations of ellipse. Okay, but we're gonna learn to identify. So identify here is intended for identifying the key characteristics of the ellipse given by the equation. And then once we have identified all of those key characteristics of the given equation of the ellipse given by the equation, then we are going to get into sketching the graph. And the intention of sketching the graph here is that we're gonna try to do it without the calculator, without a graphing device based on the identified characteristics of the ellipse from the equation. All right, so here we go. Let's look at the first problem. All right, so here we are at a given equation right here. And so needless to say, this equation here is intended to be the equation of an ellipse. But let's identify the key characteristics right out from this equation. And then from there, we're going to rely on those characteristics to quickly come up with a sketch of that ellipse. All right. And so from what we've learned from the general lecture right here, so now at this point, it's best that we recognize this equation here in a standard general form, the standard but general form. So here I'm seeing this x squared over 9 here as x minus 0. All squared. The 9 here, I'm going to recognize that as 3 squared as a perfect square. The next term here, the y squared is going to be recognized as y minus 0 all squared. The 25 here is recognized as a 5 squared. And that equals 1. So my purpose of doing this here, I would like to align this equation with the standard general equation of an ellipse, where we have x minus h squared plus y minus k all squared. This first term is over a squared, this next term is over b squared, and all of that equals 1. So I would like to align this given equation into that general but standard form of any ellipse. Okay. All right, so in that way, after pointing out how this equation now aligns with the general standard equation of an ellipse right here, then I recognize that we have h equals 0 and k equals 0. That's leading to we have the center of this ellipse is going to be at 0, 0. This is now the coefficient, the 3 squared here, indicating that 3 is that coefficient being put in the denominator of the x squared term here. And so I have a equals 3, and the b, that coefficient being put in the denominator of the perfect square, the y squared term, is 5. All right. And so now in that way right here, I'm in that specific case where a is less than b. And keep in mind again, the role of a here is that it is the coefficient in the denominator corresponding to the x squared term, and b here is the coefficient that's corresponding to the y squared term. Okay, and so in this case right here specifically, back to our reminder. So when a is less than b, then the major axis here is going to have to be the major axis with the equation x equals h, and the minor axis is going to be the other axis right here. And so from that information right here, now I'm going to use this empty board right here completely without grids, and let's quickly sketch the graph of that. Our ellipse has the center at 0, 0. Okay, and the major axis in this problem right here is going to be the axis x equals 0. But x equals 0 in our case here is this particular y-axis. The y-axis. Okay. So as an equation, it's x equals 0, but it's a line that's parallel with the y-axis. And so it is truly, in this case right here, the y-axis itself, and our center is right here. Okay. And the minor axis is the line y equals 0, which is the x-axis. So major axis and minor axis. All right. And so in this way, now I'm going to start putting in the intercept according to this general guideline. So now the horizontal intercept is going to be h plus a comma k and h minus a comma k. Similarly, the value for the v-intercept, the vertical intercept, is h comma k plus b, and the other point h comma k minus b. So on the major axis, which is now the vertical axis, we're going to have the following intercepts right here. H comma k plus b, and the other intercept is h comma k minus b. Okay, so in that case right here, in that way right here, our h value was listed on the other board being 0. Our k value is also 0, and our b value was 5. So 0 plus 5, making it 5 here. So we have one intercept right here on the vertical axis. Now the other intercept on the vertical axis being our major axis here in this problem here. H being 0, k being 0, minus b minus 5. So 0 minus 5 giving me that complete point 0 comma negative 5. Right, so these are our two intercepts on the vertical major axis. And so we set our own scale here. So 1, 2, 3, 4, and 5. And then, so right here we have that point. 0 for x, positive 5. And now the same way right here, the other points, 0, negative 5. Same scale now. Negative 1, negative 2, negative 3, negative 4, and negative 5. So about that point right there. 0 comma negative 5. So now we have tackled down the two intercepts. Our center once again is here right in at that center of the origin, at the origin. And now on the minor axis, on this minor axis right here, in our case here, I have already mentioned that it should be the horizontal axis and aligned perfectly in our case here with the x-axis here in our picture. So the intercepts are following with the following coordinates right here. So we have h plus a comma k, and the other point right here, h minus a comma k. Okay, and so again, h being listed on the other board and also a being listed on the other board. So 0 for h and 3 for a. So we're looking at 3 comma, the value for k was listed on the other board being 0. So 3 comma 0. And now for the next intercept point right here, h being 0, 3 being a being 3. So we're looking at 0 minus 3. We're looking at negative 3 comma 0, as 0 was the value for k. So now these are the intercepts that we can put on the minor horizontal axis here. Okay, so we can set our scale, and it should, most standardly, we put it on the square scale right here. So this is the scale of 1 right here that I'm looking at. 1, 2, and 3. This point right here, 3 comma 0, that's one of the intercept. One of the intercept on the horizontal axis right here, which is in our case, in this particular problem right here, it's the minor axis of our ellipse. And the other intercept, still on the minor axis right here, negative 1, negative 2, negative 3, counting out from the center. Here we're looking at negative 3 comma 0. All right. And so now with the 4 intercepts here, I can already see it start forming into some kind of oval elliptical shape right here. So of course at this point right here, the only challenge is we just try our best to draw that nice oval shape right here. And that is how we sketch our ellipse. To be more precise, with this equation right here, a equals 3 and b equals 5 right here, let's get there to put down the the foci right here. So we need a value c being square root of absolute value of 3 square minus 5 square. 3 square is a 9, 5 square is a 25. Subtracting the 2 gives me the square root of absolute value of negative 16, which is in turn square root of positive 16 after the absolute value. And now square root of positive 16 is a 4. So in that case right here, recall from the video lecture that the foci are always found right on the major axis. The major axis is here. So foci are located on this line right here. So the coordinates of foci, in our case right here, where A was pointed out to be less than B, foci are the 2 points with coordinates h, c plus k and h, minus c plus k. And we have previously just now calculated the value for c. So in that way right here, these are our foci. H, c plus k, and the other points. H, minus c plus k. Our h is 0 in this problem as identified. C here was calculated previously to be 4, and k was identified to be 0. So in that case, we have 0, 4. That's one of our foci. And for the other points of the foci, 0 for h, minus 4 because c equals 4. So here we're looking at minus 4 plus 0 for k. We're looking at negative 4. And so now all together, that one right here, 0, 4, that's one of our focus points. 0, negative 4, that's the other focus points of our. This now completes our sketch of the ellipse that was described by this equation. All right, and so now let's look at another equation right here, and of course, needless to say, it's intended to be the equation of an ellipse. But now let's identify the key characteristics of this ellipse, or of the ellipse that's given by this equation. So starting out from this equation, I would like to once again align this equation with the standard general form. So here it is already obvious that we have x minus 5 all square over, now the 36 here, it's best to think of that as a perfect square, or as the square of some other value a. So here 36 here is a 6 square. Now adding y plus 4 here, but our general standard form is a y minus a value k. So here we're looking at that as y minus a negative 4 all squared. So now I have y minus k, where k is negative 4, divided by, now this 9 in our denominator here, it's best to think of that as the square of some other number. So 9 is the square of 3, and the right hand side of the equation equals 1. So this equation now, with some simple rearrangement, has made it clear that this equation here aligns with our standard general the equation of an ellipse. And so in that way, I recognize that h, k, the center of our ellipse, is going to be 5 for that value and negative 4 from that value k. Okay. Furthermore, our a value, the coefficient before square, that's in the denominator corresponding to the x square term right here, or corresponding to the perfect square relating to x right here, that's 6. On the other hand, our b value, that coefficient before square corresponding to the y square term, or corresponding to the square of the y related expression, is a 3. So in this case, I immediately recognize by comparison that a now is greater than b. So this equation here has a greater than b. All right, so now once again, let's put down those key characteristics in a graphing space right here, and I purposely start out with a completely the brand new space right here with no grids or whatsoever. This is our x-axis. This is our y-axis. Okay, and so right here at about 5, -4, that's our center. And so there will be a vertical axis going right through that center, and there will be a horizontal axis parallel to the x-axis going right through that center that I found previously. So now in that case right here, let's quickly calculate our intercepts. And according to the general understanding here now at this point, when a is greater than b, and remember a is the coefficient corresponding to the x squared term right here. So when a is greater than b, then the major axis now is going to be having the equation y equals k. But more generally, we understand that as a line that is parallel with the x-axis, parallel to the x-axis. So a line that's parallel to the x-axis going through the center, that would be the major axis. And whichever line that's parallel to the y-axis, having equation x equals h, will be the minor axis. And so keeping that in mind right here, right at this center, the line that's parallel to the x-axis is going to be our major axis in this case right here. Okay, and so I have this line y equals -4. This line is the major axis. Let's label that. This is the major axis. And this line right here parallel to the y-axis in this case will be acting as the minor axis right here. Okay, and so now we are ready for putting down the intercept. So let's put down the intercepts on the major axis first. The formula for calculating it, h plus a comma k, and the other points, h minus a comma k. All right, and so in this case right here, our h was listed on the other board being, and it's right here, this is our h value, and so it's 5 plus, and our a value was 6, so that's making it 11. So 5 for h, 6 for a. K was -4, so I put -4 here. All right, and now for the other point, h minus a, 5 for h, a is 6, so now I'm looking at 5 minus 6, -1, and k value remains the same, -4. So these are our two intercepts, but this time on the major axis, which is the horizontal axis here in this case. So with our scale now being just this big for a 1 right here, then I'm going to go 6, 7, 8, 9, 10, 11. So right here, we put down our one of our intercept on the major axis. Okay, and similarly, here's -1 comma -4 on the major axis. -1 is about here. This is the other intercept. -1 comma -4. All right, and so that's how we found the intercepts on the major axis. Let's now turn our attention over to the minor axis, and let's look for the intercepts. Okay, so in this case right here, the coordinates reading generally as h, comma, k plus b, and for the other point, it's h, comma, k minus b. All right. And so now we have listed h being 5 here, and k being -4, but plus b on the from the other board. I have written it down right there. B equals 3 in our case right here. So here in this case, I'm looking at 5, comma, -4 plus 3, making it -1. All right. And for the other intercept, once again, still on that vertical axis, but now being regarded as the minor axis of our ellipse here. We have 5 for h, k being negative 4 minus negative 4 minus 3, making it negative 7. All right. And so now we are ready for putting down these intercept points right here. So 5, comma negative 1 is a point right here. That point is one of our intercepts on the vertical axis. Okay. So it's negative 4 here, negative 5, negative 6, negative 7. Here we have another point of ours right here being 5, comma negative 3. All right. All right, and so now in that way, now we are ready for getting down our ellipse. So our ellipse looks as following. All right, and of course I am not an artist here, so my ellipse will never be a perfect looking one right here, but obviously it shows that it's the longer side is the horizontal side being parallel with the x-axis, and all of that is due to the value a corresponding to the x squared term is the larger value, and the value b corresponding to the y squared term is the smaller value. Okay, and let's now quickly calculate c so that we can put down our foci, and once again foci should be found on this major axis here. All right, so now back to the formula. To calculate foci, we first need a c value. C equals the square root of absolute value of a squared minus b squared. And so here in our case, with a being 6 and b being 3, a equals 6, b equals 3, we're looking at absolute value of 6 squared minus 3 squared in absolute value. And that's now making it, now it's square root, absolute value of 36 minus 9, 27. And that now gives me square root of 27. Okay, and square root of 27 here is simply in reduced form here. It's just 3 square root of 3. Numerically, at about 3 decimal places, 5.196. All right. All right, so our foci in this case are calculated through the following formula. C plus h, comma k, and the other points minus c plus h, comma k. All right, so in our case right here, c was about 5.196, plus with h being a 5 right here, I'm looking at about 10.196, comma k being negative 4. And for the other points, c being 5.196, with negative of that plus 5 for h, we're looking at negative 0.196, comma negative 4. All right. So these are our foci. So negative 4 for the y value, meaning those 2 points are once again consistently on this major axis right here. And so 10.196 is about right here. Okay. And I'm not an artist anymore at this point right here. So that's one of our foci. And the other foci, negative 0.196. 0 is here, negative 0.196 is right about there. All right, so these are our 2 foci. I put an X here, making it a little easier to recognize. All right. All right, so at the end of our example 1 right here, we came down with some quick tips and tricks right here. All right, so with our equation now being in the general standard form right here for an ellipse right here. Now these coefficients, we've been saying it out loud of a and b, but now let's think about it this way right here. It's not important about the name of these coefficients being in the denominators of the x squared term and the y squared term, but the idea is this, once again, the point now is that when the coefficient underneath or the coefficient at the denominator of the perfect x square term right there being larger, because any one of these two perfect square has a coefficient in the denominator. So if the coefficient underneath or in the denominator of the perfect square x term being the larger one, then in that case, and that's why we've been writing A is larger than B. But if that's the case right there, right, then keep in mind the more important one is the major axis is parallel to the x-axis. It's not necessarily exactly the x-axis itself, but it has to be the major axis parallel to the x-axis. And so needless to say, of course, the minor axis has to be the other axis being parallel to the y-axis in this case. And then so once again, a little further, now in case that A is less than B, or now the intention here is that the coefficient that's put in the denominator of the perfect square y term right there, the perfect square y term, then that means the major axis, see, the coefficient B here is the larger one, but it's put under the perfect square y term. So that means the major axis must be parallel to the y-axis. So that's some quick little experience right there that will help us, get the problem done in a much more effective way right there. All right. All right. So now we're in another example right here, and let me now call that example 2 right here. It's still the same exact instruction with the example 1 we have done earlier. But from this problem here, hopefully we'll learn also a new skill set right here. So let's identify and sketch the graph of, and allow me to show the following equation. So let's look at the first equation. All right, so the equation we're given now is 4x squared plus 9y squared minus 32x minus 90y plus 253 equals 0. So the challenge of this problem now is that, yes, it's the same instruction. We want to identify and be able to sketch the graph of this equation. But so now this equation here is no longer clear to be what kind of graph that is. Okay, so what matters for us here, if we want to see that as a circle, we have to be able to make it look like the equation of a circle. In this particular lesson, we have learned about ellipse. If you want to sketch the graph of this one as an ellipse, we have to be able to make this equation to look like the equation of an ellipse. And that's the point. So the real intention of this example problem here is that a lot of times where we are given an equation that is not so trivial, right? At this instance, we are not able to see whether it's the equation of a circle or the equation of an ellipse. That's our responsibility right here, to turn that into the appropriate one so that we can identify the key characteristics and eventually get the appropriate graph. Okay, so for now, the starting point here is to get some algebra done right here. Observation is telling me that we got some perfect square x term, 4x squared with a coefficient, a perfect square y, the 9y squared term right here, and some x term, some y term right here, and a constant term. Okay, so with some algebra, I'm going to do the following. I am going to bring the constant term to the opposite side. So for doing that, I'm going to subtract 253 on both sides of our equation. So now that will produce 4x squared plus 9y squared minus 32x minus 90y, but equals minus 253. So what I have just done, I brought that constant term to the opposite side. And now I'm going to purposely regroup all of the x terms together, including the x squared term and the x term. Let's regroup, reorganize these terms here. So I'm grouping the 4x squared and the 32 and the minus 32x together in one group. So what I'm looking at now is 4x squared minus 32x being grouped together. And here I'm looking and add with another group right here, being 9y squared minus 90y being grouped together. And all of that here equals minus 253. The next step I'm about to do now is I'm going to factor out in each of these groups right here. I'm going to factor out the leading coefficient. So the leading coefficient here in this group is a 4. I'm going to factor that out, making it x squared minus 8x. For this group right here, I'm going to factor out similarly the leading coefficient 9 right here, making it 9 times y squared minus 10y, and all of that there still equals to negative 253. All right, and so now at this point where observation is telling me that inside of this pair of grouping parentheses, if I can just simply add a 16 to that, that's why I'm writing that in red ink right here, simply adding a 16 to that will make this setup right here inside of my first grouping parentheses is a perfect square. And so completing the square is a skill we've learned through algebra long time ago, long before we entered this course right here. So I purposely added that 16 right here to complete the square inside of our parentheses here. But so we cannot just, in the rule of algebra, we cannot just brutally add a number. So in that way, adding a 16 to the inside of the parentheses means there's always a 4 multiplied with that 16. So 4 times a 16 is a 64. I am going to add that 64 to the other side. Okay, and so once again, I added a 16. I decided to add a 16 inside of this grouping parentheses to complete the square. But that means at the same time, I need to add 4 times of the 16, which is a 64, to the opposite side as well. Because really, when we distribute out the 4 right here, then we're looking at 4 times 16, making a 64 on the left-hand side, and that other 64 on the right-hand side will again cancel out and undo that work. But we purposely added in, so that's why I chose to add 16 here, okay, and then 64, adding 64 on the other side. All right, and so similarly, in the same way how I'm doing it, this pair of grouping parentheses is here. I got y squared minus 10y. Okay, I'm going to decide to add 25 right here to complete the square inside of our parentheses here. But completing that square right here, but adding that 25 inside of the parentheses means now 9 times 25, I'm going to need to add a 225 to the other side of our equation. All right, and so now let's put it all together. I keep mentioning that the purpose I've been adding those values inside of the grouping parentheses in red is because those will make a perfect square. So the left-hand side from our previous equation now will become the following. The left-hand side of our will become 4 times x minus 4 all squared plus 9 times y minus 5 all squared. Okay. The right-hand side is just a matter of adding up these values here. That all together makes 36. All right. And so now just one more trick. The equation here is almost looking like the equation of an ellipse. It has some coefficient, and then with a perfect square, another coefficient with a perfect square, and equals a constant on the right-hand side. I'm going to decide to divide both sides here by 36. All right. That now will make it the right-hand side equals 1 exact. On the left-hand side, this first term, this perfect square term, the 9 reduces with the 36 in the denominator, making it over 4. So we had y minus 5 all squared over 4. Plus, now with the 4 reduces with the 36 here, that whole term here becomes x minus 4 all squared divided by 9. And so now clearly it's the equation of an ellipse right here. And we can further rewrite this as x minus 4 all squared over 3 squared plus y minus 5 all squared over 2 squared equals 1. All right, so now this is so clear that the final equation we have arrived at is the equation, the general equation in standard form of an ellipse, where we have center of the ellipse is at 4, 5. Okay, between the two values here, a is larger. The coefficient in the denominator of the perfect square x term is larger, and so in that case right here, I'm going to know that my ellipse has to have major axis parallel with the x-axis. All right, and of course minor axis is going to be parallel with the y-axis, needless to say. And then we have from our picture over here, yes, a equals 3 and b equals 2. All right, and so now the intention of this problem is to show how we can bring an unrecognized equation into an equation where we can recognize that as an ellipse. And now after identifying the information right here, I can quickly, without too much explanation, because you have seen that skill in the earlier example. So now I'm going to just speed up on the process right here. All right, so in our graphing space, center is here, 4, 5. That's the center of our graphing, that's the center of our ellipse. And now, as I said, major axis is parallel with x-axis, so it's going to be, this is where the major axis is at. Okay, and then on that way right here, so we're going to have the intercept. And so now the intercept will always be, as another shortcut of that, it's 3 away from the center on each side. The center here on the major axis is 3 away on each side. So 1, 2, 3, 1, 2, 3. These are the intercepts on the major axis right here. Now the minor axis is here. Okay, and so that B right here is indicating from the center, the intercept is being 2 values away from the center point. All right, and so now that completes our ellipse. All right, and allow me, since my picture is too tight right here, allow me to skip putting down the foci, where foci are expected somewhere on this major axis right here. But that's how we can quickly sketch the graph after identifying a non-standard equation. All right, so here we have another equation, which is at this point right here, it's not so clear whether it's the equation of a circle or equation of an ellipse. But so now, in this way right here, once again, similar to the earlier equation we brought in the same example here, what I'm seeing here is we got some perfect square term. And that brings up a sign about the equation here can potentially be the equation of an ellipse right here. Okay, and so algebraically from this equation, I am going to divide both sides by 100. The reason we don't have to do as much as the earlier equation now is that we don't have the linear x term, we don't have the linear y term, and the constant term was already on the right hand side. And so without that, then we can just simply treat the x square itself right here as already a perfect square for x with a coefficient, and we got a perfect square for y with a coefficient. And so in that way, I have already gone through, I have already had the equation here in a perfect square and another perfect square with some coefficient. And so in that way, I can just jump immediately into that step where I'm trying to make that right hand side equals 1. So in that way right here, my next equation becomes 4 reduces with 100, giving me x squared over 25. 25 reduces with 100, gives me y squared over 4. And that equals 1. And so now this is the equation for an ellipse. And I can just now easily rewrite that as x minus 0 r squared over 5 squared plus y minus 0 r squared over a 2 squared equals 1. Okay, so now easily I can see that the center of this ellipse is at 0, 0, according to those information that we have identified. Now a is here and b is here. The coefficient in the denominator of the perfect square x term is a 5. So I call it a equals 5. The coefficient in the denominator of the perfect square y term, I call it b. That equals 2. So now we're in that case where a is larger than b right here. But the point now is that means the major axis of the ellipse has to be parallel with the x-axis. So let's nail that down. Keep that in mind right here. Major axis is parallel with the x-axis. All right, and so now we have just about enough information to get ready to get it done like that. And I'll come back with this information a little shortly. All right, so now let's put it on the sketch. The center is at 0, 0. All right, and let's set our scale right here. That's the scale of 1. That's 1. All right, so with the center being 0 right here. Now, so the major axis is parallel with the x-axis. We made it clear from the other board. And so now, in this case right here, since the center is right on the x-axis, so this x-axis itself is now the major axis of our graph right there. Okay, and so now the value a being 5 indicates, so now another way of seeing the value being a being 5 indicates that we are, from the center, we are 5 spaces away on each side. One, two, three, four, 5. 1, 2, 3, 4, 5. That's how we put down the intercepts on the major axis. On the major axis, each intercept is 5 spaces away from the center. Okay, and so we've got the intercept on the major axis. And now with that same scale right here, b value was listed being 2. That means, so I'm showing a faster way of, instead of going through the coordinates point right here, but that means on the minor axis, which is now parallel to the y-axis, or being on the y-axis in this particular problem right here, then the intercept on the minor axis is 2 spaces away from the center to each side. So we got 1 point right here and 1 point right here. So that's making it 0, 2 up there, and this down here we got 0, -2. And right here that intercept is a 5, 0, and that point right here being the intercept, -5, 0. All right, so our ellipse is going to look as following. All right, and that's how I have completed the sketch for that ellipse. And so at the end of this example right here, aside from being able to rewrite the equation so that we can bring that into the equation of an ellipse right here by completing the square, we additionally learn a little bit of a tip right here that with our equation of an ellipse right here, then a represents the distance between the center, okay, and each intercept, okay, on the horizontal axis. The horizontal axis means the one that's parallel to the x-axis right here, because that's where we put a as the coefficient. And similar meaning with b right here. B means the distance between the center and each intercept on the vertical axis. All right, so that will quickly help us find out where the intercepts are on each of the axes is here, instead of going through the coordinate point like that. All right. All right, so now we're looking at our third example over here, where it brings in another way of how we can apply our understanding about the equation of an ellipse right here. So in this problem, we're asked to find the equation of an ellipse with vertices 0, comma, plus or minus 6. So vertices is a new term to be learned in this example right here. Okay, and further, this ellipse here has foci 0, comma, plus or minus 2 square root of 6. Okay, so we know that it's an ellipse, but we want to complete the equation. Okay, and so as a goal to remind, our equation here generally is x minus h all square over a square plus y minus k all square all over b square all equals 1. So once we can successfully identify the value for h, the value for k, the value for a, and the value for b, and we're good to go with that equation. Okay, vertices here for an ellipse, vertices refer to, let's say, when you have an ellipse and it goes like this, the longer side right here, those intercept along the longer side are the vertices. So that's the these two are the vertices. Similarly, when your ellipse is longer on the horizontal side along the horizontal axis, those intercepts are the vertices. All right, so that's some quick explanation about the vertices right here. We don't call these the vertices. We don't call these the vertices. And so now with the given information about the vertices is here, and really this way of reading it, it means we have two vertices. One of them is a 0, comma, positive 6. The other one is 0, comma, negative 6. Both of these vertices have x coordinates equals 0. So that immediately tells us that if we're putting on a picture over here, we have a vertices at 0, comma, 6 and 0, comma, negative 6. This point right here, 0, comma, 6, 0, comma, negative 6. That's how we're understanding it about it. So the picture, as I explained earlier, these vertices are the intercept on the longer side or on the major axis. So the picture has to look like this. All right, that's the expectation now. At least we nailed that down. That's the expectation. And so further, as a consequence here, the vertical axis here has to be, the vertical y-axis here has to be the major axis. So y-axis is the major axis. Major axis being the y-axis, simply because the x equals 0 is the major axis. So we read it that out right out from our coordinates of the two vertices, like that. All right. And now, in that way, that so center, we have been experienced enough up to this point. Center is always exactly halfway between two vertices. Okay, center is exactly halfway between. So in that case, center has to be exactly 0. 0 for x, needless to say, but now 0 for y. So now we trace down. Center of this has to be 0, 0. Okay, and so let me swing back to the other board. That means with this general equation here, we have found out some information, and our equation is halfway completed. We got x minus 0 to be now x squared over a squared. Okay, plus now k should be 0 because the center is at 0, 0. So y squared over b squared equals 1. Okay, so we're getting closer to our complete form of our equation. Let's now find out what a value is and what b value is. The vertices is given here again. Is indicating that on this major axis, and I mentioned this the tips and tricks from right at the end of example 2 right here, that the value b, now in our case right here, the vertex, since we noticed that the major axis is along with the y-axis, that means b is the larger value, larger value, and that means each distance right here has to be b, and that's now indicating that b equals 6, because once again from that information we've learned, a or b represent the distance from the center to the intercept, from the center to the intercept, from the center to the intercept on each axis. So now on this axis we have already known the major axis here, right? From the center out to each of the vertices right here, it's -6 and +6. So this distance from 0 to 6 right here and 0 to -6, that makes me conclude that b has to equal 6. Okay, and so now in our equation I have found out a value for b. So it has to be x squared over a squared plus y squared over 6 squared equals 1. Okay, so the value for a is the last piece of information we need to identify. So now let's look at foci information. Okay, now foci information. Foci is on the major axis again. So that's why it's been reading for foci 0, +2 square root of 6. That's one of the foci. And the other point, 0, -2 square root of 6. Okay. So in that way, I can see that according to the formula that we've had, when b is greater than a, or when a is less than b right here, when a is less than b, the foci here is corresponding to h, c plus k, and correspondingly h, -c plus k. That's the general formula for coordinates of the foci. Okay, but then we knew from earlier that so now our center h, k is 0. So that means really our foci in this case, right here, in this particular problem, has to be just simply 0 for h and +c for that one of the foci, and then comma 0 for h -c for the other foci. Okay, so now in that case right here, it leads down easily that c has to equal 2 square root of 6 and -c equals -2 square root of 6. So that means it leaves a little clue for us right here. So now c equals 2 square root of 6, or precisely bringing that 2 inside the square root right here, we're looking at square root of 24. All right, and so c further is understood to be the square root of absolute value of a squared minus b squared. Okay, and we have already found b being 6 right here. B is being 6, and so in that case I'm looking at square root of so a squared minus 36 in absolute value to equals c. Okay, but c was found to be square root of 24. So from that way we can easily square both sides, and by the way, let's just write it as square root of 24 equals the square root of absolute value of a squared minus 36. Okay, we can now square both sides of that equation, leading it down to 24 equals the absolute value of a squared minus 36. Okay, and we know for sure that because the major axis is on the vertical side, so the value for a here has to be smaller. So that means this absolute value right here, the square of a, is smaller than 36. So that absolute value right here has to be as following. With our absolute value, it must be 36 minus a squared. Okay, algebraically. And so in that way right here, now we can just simply rearrange this equation, making it a squared equals, now I'm subtracting 24 to the other side and adding that a squared to the other side. And so that's making it 12. All right. So a squared equals 12. And I don't think in this problem I have to go all the way down to a right here, because a squared is everything we need. So a squared equals 12. We have found it. Okay. So in that way, our final complete equation appears as following. X squared over 12 plus y squared over 36 equals 1. That is our equation of the ellipse that satisfies this given information.